Okay, sorry for the delayed start. We had some technical issues, so hopefully they're all fixed now, so we can get started. So I have the honor of hosting Professor Ashif Iqbal. He's from the School of Computing and Augmented Intelligence at ASU. He's an assistant professor, and also I collaborate with him. And his area of research is inverse modeling, materials informatics, and we collaborate quite a bit on microstructure modeling and AI. So hopefully he can show some of those results today. Uh, Ashif did his PhD at Texas A&M University and his bachelor's at IIT Kharagpur. So, and then he has also won a number of awards. You can check the details on the file. So without delaying further, let's welcome Professor Iqbal, and the floor is all yours.
Thank you. Thanks, Ankit, and thank you everybody for showing up to in-person seminars. I do seminars in my school, and we are having a hard time. So first of all, thank you everybody showing up here. My name is Ashif Iqbal. I joined ASU a little over, I think it's almost 3 years now. It's August, so I can say 3 years. And I'm in the School of Computing and AI, and to be specific, I am in industrial engineering. And that's what my background is. And you'll see I talk a lot about manufacturing in whatever I do, because that's very much at the core of my research. But that also opens up lots of interesting opportunities, and that I hope I will be able to give you an idea as to why I am in School of Computing, even though my research is significantly focused on advanced manufacturing. And please feel free to jump in, ask any questions if you have while I'm making the presentation. And instead of going into depth of one single topic, I thought it might be a good idea to give an overview of what are some of the interesting problems that we can solve in materials and materials characterization by using this data and techniques in AI and data analytics. Okay. All right, so this is my team. Of course, I take credit for whatever they are doing. They're definitely, I think, in the Zoom room. So first of all, thanks to all these amazing people who do all the hard work and listen to my criticism, and then I make presentation on that work. And of course, thanks to the funding agencies who support my work. Let me take a detour a little bit here and talk about where I am, where my research fits, and then we'll try and go into today's specific talk on advancing and accelerating characterization. So the plot here, this shows the US Industrial Production Index. That's basically a measure of how much productivity output is happening. And you will see something very interesting. This is on log scale. So you see right around this 18th century, end of 18th century, you'll see that there's a sharp increase, almost an exponential increase in US productivity. Can somebody guess what is this major milestone? It was the first industrial revolution, absolutely, thank you. So that brought in mechanization into US for the very first time. And then if you see this exponential growth sort of continued throughout, and that was largely because of the second and the third industrial revolutions that brought in mass production and automation. Now we are almost in 21st century. We are at the cusp of something very interesting. We call it smart manufacturing. I don't think a lot of people have clarity on what exactly smart manufacturing is. There's a lot of definitions going on. What exactly is there in smart manufacturing that makes it different from automation and mass production? So let's take a look at what NIST's belief is or definition is on smart manufacturing. It's about the integration of advanced manufacturing processes, sensing techniques, and data analytics and AI. That's what really makes manufacturing smart. We were able to do sensing in 1970s. We were able to do data analytics almost 20, 30 years ago also, and advanced manufacturing has been there forever. It's this intersection of these three widely different domains that makes it smart, that makes manufacturing smart. And I've been lucky to work at this intersection I was trying to say that throughout my PhD career and also as a faculty, I've been fortunate to work at this nice intersection, especially in terms of advanced manufacturing. My research is focused on hybrid methods that brings in additive and subtractive manufacturing together. I've worked on developing cyber manufacturing platforms where systems can operate completely autonomously from design to manufacturing to monitoring and control. And of course, that brings in a bunch of different types of sensing techniques and AI, and also on more advanced techniques like nanolithography for creating patterned surfaces. From sensing and measurement standpoint, I have worked on integrating different types of sensing techniques into manufacturing systems, different types of measurement and characterization techniques such as electron microscopy, EBSD, to the point where I sometimes say that 70% of my PhD time was spent on looking at these microstructures and actually figuring out what the microstructures are by doing etching, polishing. And the third aspect of my work is data analytics, where I focus on graph analytics, causal inference, active learning, and inverse problem, which is the topic of my today's talk. Right, so this is smart manufacturing, but what makes smart manufacturing so interesting? I'll give you a couple of pointers here. First one is manufacturing contributes roughly $2.3 trillion to the US GDP. That's roughly 12%. And if you think about any big tech giant right now, all of these tech giants have their own smart manufacturing test beds that they are working on to advancing manufacturing. But the real opportunity in manufacturing is the data opportunity. And this is still a slightly older statistic, but even at that time, manufacturing was producing roughly 1.8 billion gigabytes of data. That's more than government and communication and media combined. A lot of this data is not used. In fact, statistics say that roughly 25% of the data is currently harnessed in doing any decision making. But the real question is, what can we really do with the data? And that's the focus of my talk today and my research as well. So I'll give you some examples from my past life. This is where I was working as a PhD student on a DED process. It's a type of additive manufacturing process. What we did was we actually installed a bunch of sensors onto this machine, and we were recording the process using vibrations, forces, acoustic emissions, and also high-speed imaging. And the whole idea was to see if we can use all of these synchronized data sources to figure out if something is wrong with the parts that we are manufacturing. So we did some preliminary studies. We looked into different types of sensors, and we were able to sort of like do a bulk analysis that, hey, if you use this type of process condition based on the sensors, I can tell that this is not a good part. This has some type of defects. And then we were able to cross-validate by going into the microstructures and observing the microstructures. We also use this high-speed videos from the process to track what is happening to these powders that we are depositing into the build. And based on tracking these patterns, we were able to see how much of this powder is being wasted, how much of that is actually going into the build, and use that analysis to see if we can predict the porosities. Because if you have more spatter, that means more powders are getting into the build, but is ejected out, leaving a void. So that leads to porosities, and we were able to predict porosities by just tracking these videos. A lot of my work actually focused at that time which is also the traditional machine learning language that we know now. You have some type of input, which we call as sensor data X, and then we make some type of a model. You can think of as simple as deep learning. I'm saying simple because that's more common nowadays. But we build a model here, F, and then we predict the response, Y. That's the traditional machine learning models. But over time, and this is my philosophy, and this is how I started to think, that this is not the natural causal effect. Input is not sensor data. Sensor data is actually an output of something that is manifested in the process. So really, we are trying to figure out what are the inputs that is creating these sensor measurements. And that led me to reformulate all of these problems into something called an inverse model, where your Y is your input that is unknown. There is some transfer function, some process, which could be very, very complicated. But because of this transfer function M, we are observing these sensor measurements. If we can solve this inverse problem, we can obtain y. Problem with solving inverse problems is that they are ill-posed. The solutions might not exist, and depending on the problem you're trying to solve, the solution might not be unique. And if it's noisy, it might be too sensitive to the noise in the measurements. And so we try to develop methods by which we can add some physics knowledge so we can regularize the space. We can say that, hey, the solution space is much more restricted than what you might be thinking. And that's basically a very, very basic idea of an inverse problem. All right, so given this idea of inverse problems, I want to go back to today's topic and talk a little bit about the characterization aspect, why characterization is challenging right now. And I will focus on two things specifically: mechanical property testing and learning the physics of the process. I'll talk about two examples: tensile property measurement and then infiltration dynamics using inverse problems. And I'll show why existing inverse problems are not enough in solving these characterization problems, and why we need more advanced techniques. And then depending on time, I'll go and talk a little bit about some of the work that I've been doing in the microstructure space. All right, so characterization of materials. The way I look at any materials discovery problem or design problem is that you start with some idea about what the material is, right? This is where you would probably do some simulations, you have some prior knowledge, and based on that, you will try to come up with some initial iterations. Then you have manufacturing. Now, thanks to additive manufacturing technologies, now we can literally manufacture anything we want. And this goes from traditional materials to functional materials to graded materials. Third aspect is characterization. And then this is where we are measuring the mechanical properties, we are measuring the microstructures, and we are trying to verify if we are able to manufacture or synthesize whatever we were looking for. Now, this is where the real challenge is right now. No matter how fast we are in terms of computational power, in terms of AI, somebody still has to go and do mechanical work. Somebody still has to do polishing and etching and spend hours on doing imaging. That takes a lot of time. And I know I don't think there's anybody else who can understand more than this group of people, this challenge. So the general question is, we understand characterization is a big bottleneck right now in the material discovery space. How can we use data to accelerate some of these characterization? Okay, I'll give you a couple of examples. So before I give some couple of examples, how does this fit into industrial engineering and manufacturing? So industrial engineering manufacturing, we typically call it certification and qualification. Whatever we are manufacturing, we want to make sure that they meet the desired properties or desired specifications before they actually go into operational phase. So we focus on estimating the mechanical properties, thermophysical properties, measuring the quality. This could be GD&T, geometric and dimensionality measurements. And then we also look into characterizing the microstructures. I have a couple of examples that I'm currently working on, so I'll give some ideas here. This is an electron backscatter diffraction. And we can use this EBSD technique to measure the microtexture and the microstructures. In terms of mechanical testing, we currently use tensile testing to measure the mechanical properties. These are the gold standard right now for microstructure and mechanical testing, but there are problems. EBSD, again, is limited to smaller regions, and it could be very, very expensive, so we cannot take it beyond lab scale. With tensile testing, we have to manufacture hundreds of these dog bone samples and then break individually each of them. And so it is definitely expensive and destructive. The trend right now is on-demand manufacturing. The idea is just like you send a photo that you want to print to Office Depot and they print your photos, you'd be able to send your designs to a 3D printing Office Depot, and then they can prepare your design and have the part ready, and you can go and pick it up. But to have this reality come true, to have this vision come true, you have to be able to do testing in a way that doesn't require destructive testing or is not expensive, right? So how can we replace? So the main question is, if we have to accelerate characterization, how can we develop techniques that are based on data that can potentially replace or we can also say augment EBSD and mechanical testing. Two different examples. Another area of research is more fundamental, where we are focused on understanding the process physics. We have data coming from different processes. There are some processes which are much more complex. We still don't understand them. Some that we understand, but we still don't completely rely on them, right? So the question is, how can we use data to guide scientific discovery of engineering systems? This is an example of a material system where we're looking at the stress strain profiles in the black. And if we use different material systems, you would get completely different response. So by just looking into the data, is there a way that we can tell what is the correct physics or the correct material behavior that we can use to simulate this material? Another example that I'm working on is the capillary infiltration dynamics. And again, the problem is we still don't completely understand the physics of capillary infiltration. There are some fundamental physics on that, but that changes completely as you go from one material system to another material system. So the question is, how can we use data to guide what is the correct physics? How do we estimate these parameters? How do we know which one of these is active, which one of this is not active? So that's the general overview. Now let me try to pose these two questions. First is, how can we accelerate and scale up material characterization in terms of mechanical testing, in terms of microstructure analysis? That's the first part of this talk that we'll focus on. And then we'll jump on and see, can we use data, measure data to discover process physics? And I'll show you one example in infiltration problem. Okay, any questions so far? Yes.
Can you say the difference between additive and subtractive manufacturing?
Yeah, so additive, you can imagine when you stack up layers on top of each other. So that's more of additive. And the good thing is, now that you can stack up layers on top of each other, you can create these layers the way you want. Subtractive is doing the reverse way. You have a big block and then you selectively cut it. But when you selectively remove material, you have a problem, because if you want to remove material from inside, we still don't have a technique that can remove material from inside. And so that's why subtractive is a little bit more limited.
Thank you.
Yeah. Okay, so let's go back to the first example where we're talking about this tensile testing. This is the gold standard right now. We manufacture dog bone samples, we break them, we measure the stress strain profiles. Challenge, it's costly, it's slow, and it's destructive. An alternative measurement is to do indentations, measure the force displacement profile, which is fast. It's really cheap and it's non-destructive. You literally make a micrometer depth dent, and which you can polish or machine out easily. If you can use these force displacement measurement to somehow predict the elastoplastic properties, we might be able to solve the problem. We might not have to use tensile testing, right? So right now, there are physics simulations that can take elastoplastic properties and simulate the force displacement. The question that people are asking, or people have asked, I'm not the first one, can we reverse this? Can we go back from force displacement to elastoplastic properties? Of course, sounds very interesting. If I can do this, I can get rid of tensile testing. So the very first paper, if you look up on this topic, was in around 2001. Subra Suresh from MIT and his group, they worked a lot. There's an extensive amount of work around that time, and they try to first of all simplify the problem a little bit. These are functional curves. So force displacement is this blue curve. Stress strain is also this blue curve. But you can translate these functional profiles into some parameters. That's what they did. It was very useful. And so they said, instead of predicting these profiles, why don't I predict these quantities, right? So now you have these quantities that you can easily measure on the left-hand side, on the right-hand side, and then you would want to predict these quantities. And so if you go to the paper, they actually came up with empirical formulas that look something like this, about 8 of these. So if you have indentation measurements, use these formulas and you'll get the stress strain profiles. Sounds interesting, right? And they work great. If you look at the examples in the paper, they work amazingly. Problem is, if you change the material system, they don't work. And it makes sense because these are trained on very specific data sets. So the only problem is, or maybe the problem is the generalizability. And the second problem that we realized later on, if you have measurement noise, right, these models would not be able to handle those measurement noise. So fast forward almost 18 years, and this is from Georgia Tech. Amazing group of people from mechanical engineering to statistics to material science. They actually tried to solve this problem. The method was developed way before they used it, but they actually used something called a Bayesian approach. And the idea of Bayesian approach is that any uncertainty that you have in the measurement, you can use that uncertainty and translate into your predictions. So now, instead of getting a point estimate, this is what I would call a point estimate. If you solve this equation, you get a single value for sigma, right? And that doesn't capture the uncertainty. But if you do a Bayesian approach, phi, in all of my discussions from now on, phi is a probability distribution. So if lambda is my unknown quantity, which is my sigma in this case, q is my measurement, then I can obtain a distribution on my unknown quantities. And that sort of captures this noise very well. And this works great. You can actually see an example here. So this is a stress strain profile that they recovered. And the estimate is, you can look at the dotted line or the solid line. Both of them are completely fine. The one with circular markers, they are the true data. So you can see it's somewhere here. And their mean value also is very, very close. But in addition to providing you a mean estimate, it also provides you a confidence interval, which is this gray band. Tells you that this is the uncertainty. Now, here is the problem with a Bayesian approach. If you look at any material system, if you manufacture consecutive material, if you print a bunch of dog bone samples, you cannot expect every single dog bone sample to have the same elastoplastic properties. They would not have the same stress strain response. There would be some variability from material to material. So there is an inherent variability in the material itself. Problem with this type of an approach is that it assumes the variability is coming from measurement noise and not from the variability in the material itself. So what happens is, and this is theoretically, if you collect large enough data, this confidence band will narrow, and at the end, it will basically collapse at the mean value. So it's counterintuitive. I was actually trying to see if I can capture the variability in the material. Well, at the surface, it looks like it's capturing the variability or uncertainty in the material, but it's not. It's actually transferring all the variability in the material to the measurement noise. And that's problematic. So the main question that we're trying to answer here is this. Any real system that we are looking into, there is variability inside the material itself. So if you look at force displacement profile, and this is real data based on multiple dog bone samples, you would get completely different, not completely, but widely varying force displacement profiles. And if you look at the stress strain response, they're also widely varying. So the real question that we really want to answer here is, if I have force displacement measurements, and there is some variability in the force displacement measurement, can we use that knowledge to figure out the true elastoplastic properties and the variabilities therein? Right? So as opposed to just going from this to this, I want to work in the pi space. Pi space is my probability space. I want to go from the distributions of this to the distributions of this. And that's what we call as a stochastic inverse problem. All right, so I would not bore you with the math, walk very quickly here. If you're familiar with a Bayesian approach, the way it starts is, whatever unknown quantity you have, the unknown quantity is lambda, you put some prior belief on that, right? and then you measure some data, and then you obtain this posterior belief. This is what Bayesian is after. Stochastic inverse problem is very much similar to a Bayesian inverse problem, except that you have an additional term, which is this denominator here, which we call as a push forward. So the first term is the prior, second term is what we call as likelihood. It's basically the data. You can think of it as the data. This push forward is what is interesting. Push forward says, if you randomly generate unknown stress strain tensile properties, this will tell you the distribution of the indentation measurements. Right? So now we have the distribution of the true indentation measurements and distribution of, I would say, hypothetical indentation measurements. And so if you can imagine, if these two matches, then those stress strain profile that I'm calling as random, they're not random, they are the true ones. Right? So we basically use different types of sampling techniques to figure out, we randomly create these stress strain profiles, and then we select those for which these two matches. And that's very, very vague answer. My student is sitting here, so he's probably laughing. But that's the intuition of how this is working. Okay. All right, so we have some models here, and then this is basically the sampling technique I was talking about. Probably skip this for the time being. I want to show you some examples here. First of all, a very, very simple example. Let's say our model is lambda raised to the power p, and we don't know this model. We only observe q of lambda. Okay, p is a parameter that is given to us. We want to figure out what is this lambda. Okay, so let's click p equals to 1. So it's a linear model, very, very simple. Prior could be anything. In this case, we are using a very, very simple uniform prior. A uniform prior basically says that we have no idea what the system is. So we do that, and we compare two models, Bayesian model and stochastic model. So B is Bayesian, S is stochastic. Both of them work perfectly fine. Both of them overlap with the data, which is what we were expecting. As you make the system nonlinear with P equals to 5, even if you have an informative prior, your Bayesian, which is the green dot, now does not match with the data. Now, but still, your stochastic model does match with the data, which means we're able to accurately capture the variability in the data. That's the easiest way to interpret the right-hand side figure. Let me show you a couple more interesting example, which is in the indentation problem. So we generated FEM simulations, and we have about 100 different elastoplastic parameter combinations. So created a bunch of data on the elastoplastic properties and the indentation measurements, right? And then the simple question is, can we use the indentation measurements, which is the force displacement profile, to figure out the elastoplastic properties? That's the simple question we are solving based on the simulated data. So the first thing I want to show you here is, how does the distribution match? We're essentially after the distributions, right? So we have three quantities, C, dP, dH, WP, WT. They have some physical meaning, but I'm going to skip that for the time being. You can see if we use a stochastic approach, the distribution very much matches the true distribution, and the true distribution is the blue one. We use a Bayesian, does not agree very well here, right? Now, it's good that we are able to match the distributions, but how about the prediction accuracy? Are we able to predict the quantities very well? So let's look at that. This same data was actually published in 2020 in PNAS, and that's the neural network model. So this is the yellow box plot that you can see here. We are looking at mean absolute error with respect to the training data size. So if you have a deep learning model, if you have a neural network model, the more data you give to it, the more accurate it will get. So you can see the error is reducing in the neural network model, right? Makes sense. Can we do better? We can do better by doing a Bayesian approach, because now Bayesian approach handles noise very well. So you're able to do slightly better. But again, because of that assumption that everything is noise, Bayesian is not doing as good as when you start assuming that the variability is not noise, but the variability is the real variability in the material. And now we are able to do significantly better even with very few data sets. So we are actually looking at the E star and sigma y are essentially the elastoplastic properties that we have extracted from the stress strain profiles. Right. So this is the first example. I'll probably maybe hold on for 10 seconds and see if you have questions. Yes, please.
Why is the Bayesian good here and not good in the other slide?
Bayesian is better than neural networks.
Oh,
Which is the yellow one. But it is still not better than, so when we are comparing the absolute error, you want it to be as low as possible, right? So the lower it is, the better it is. So Bayesian is definitely better than neural networks, but it's not better than the stochastic approach, which is what we wanted to say.
And the previous slide, Bayesian was not.
Yes, in the previous slide too. So if you, let's go back. So if I go back to this example, you really want to match this red curve here. Bayesian gives you the green dotted line, which does not match with the red curve. Okay. Any other questions? Yes.
How do you account for the variability in the material?
How do you
account for the variability in the material?
Oh, okay. Good question. So going back, this is the key here, the push forward. So remember, I said we are randomly throwing elastoplastic properties, right? That's the variability. So I'm starting with the assumption that it's completely random. And then this is what we call regularize. I'm going to restrict only to those that make sense with the data. Does that make sense? That's what I'm saying. I kind of skipped details here, but the main idea is we try to use some type of physics to regularize these inverse problems, to add more knowledge. Questions? Yes.
Sorry, hold on. So with the elasticity, when you're actually measuring it, then you're like pulling it, right? What are you measuring and how with the force push?
So you basically take like an indenter, and then you make indents. It's very, very much like this, and make indents on the surface. So it's not exactly like pulling, but it does create that response of, when material is deforming, so you're able to measure how it is deforming with the force. So it's very, very hard, at least so far, it has been very, very hard to actually completely replace tensile measurements. Still very hard to completely replace it. But if we generate more confidence that we can accurately estimate not just the mean values, but also the distributions, then we can do it. And so one of my work that I did not show today is, I'll try to, I've not mentioned it here, but one of the things that we're trying to do here is, if you look at additive manufacturing, we use different process conditions or different parameters, different materials, you'll get different distributions of stress strain. So really, if we can say that by just looking at indentation, we can recreate these different distributions, then we have solved the problem. Yes.
I'm sorry, I'm still just a little bit confused. Going back to the force implementation, right? You have your sample, but I imagine also, I'm picturing it's like a hardness test, right? You have
Yes.
like a diamond point.
Yes.
You apply force and you measure how far it moves, but then depending on where you put that indication point, when those values differ, depending on the sample size, like if you have like a coupon.
Yes.
Doing the indication like at the very dead center versus the very edge, or if you go, I don't know if you do this, but going on like
yes,
cylinder,
yeah,
it's going to be different, right?
Yes.
How is that also incorporated into that?
Yes, absolutely. So this is this is actually thousands of measurements that what you're saying right now.
Oh, so it's just like all.
Yeah, we are all looking at different measurements.
Okay, so that's all in the same sample.
Yes, this is the real data that I'm showing you.
I was thinking that's just like 1,000 different samples.
Oh, no, 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 no.
Okay.
This is one sample. You take multiple measurements as much as you can, and then we use that variability to figure out the variability in the elastoplastic properties.
Thank you.
So my question is, how is the noise affect about same noise to affect the
It's a good question. I don't have an answer to that question right now. So there are two lines of thoughts. People, before this talk, they assumed everything was noise. I am assuming everything is the input variability, nothing is noise. So we still have to figure out how we can decouple noise and the variability. And that's the hard problem. That's not easy to do because in some ways they're confounded right now, right? I don't have my future works, but whenever I do the first part of this talk, the future work is we're trying to figure out how to decouple the measurement noise and the true variability. Right, so I'll move a little bit faster. We have 15 minutes. I'll try to be a little bit fast here. And second problem, how can we actually use this same idea to understand or learn some unknown process physics? And I'll try to make this as simple that makes sense to me, and then we'll go from there. So let's say we have an underlying nonlinear dynamical system, x dot equals to phi of x times some coefficients. And I can think of phi of x as some library of physics. And I'll give you examples to make sense of what it actually means. A library of physics basically could contain these first order term, second order term, partial terms, differential terms, anything you can imagine, right? I'll give you an example first, and then I'll come back. So this is a load curve Volterra system, which is also called a predator prey model. You have U dot V dot. One of them is accounting for the rate of change of prey, and the other one is for the rate of change of predators. Right? This is a known differential equation. I can transform this into a slightly different form where U dot and V dot, this is equal to a library of physics. So if I don't know the true physics, I don't know. So U dot depends on U and UV, right? I don't know that. What I can do is I can say that these are all possible potential terms that can depend on, right? And if I know the coefficients, this is written here, and if you solve this, you'll get the same problem, same differential equation. But if I don't know the differential equation, I'm going to make all of them unknown. So you basically, when you don't know the physics, you basically construct a library of all possible physics, right? And so that's what we do here. And then we can use standard loss minimization techniques to figure out the coefficients, this coefficients here, and then that will give you the differential equation or the dynamical system. This was done for the first time in 2016 by Steve Brunton. And then there is a lot of development. If you look at last 6 years on this topic on learning the physics, there's a significant amount of papers, and they all solve very, very complex problems in learning the dynamics. But I'll show you some problems with existing methods, and I'll show you why stochastic inverse approach can solve this problem. Okay, so we'll again work with load curve Volterra system. You have two equations here, and we construct a potential library that has all potential terms here, and then these coefficients are unknown. So the idea is, can we observe some data on U and V, or U dot and V dot, and can we figure out these coefficients? Okay, so let's go quickly and see what we can do if we use the very, very initial work. This is a true system. This is a system that you recover if you use the, I would call a vanilla approach. No modifications to the very initial work. And you can see it doesn't work that great. So why was this published? It's published because it works on the example that's in the paper. If you change the system, it does not work. Okay, so people realize this. And one of the problem with this specific method is that the same problem that we talked about with Subra Suresh's work, they're deterministic. They assume that there is no noise in the system, or at least, noise is not enough to influence your results. So fast forward to 2022, this is very recent, they actually developed a Bayesian approach for solving the same problem. You have loss function, but you take a Bayesian route to solve it. And I would not go into the details, but they developed very ingenious priors. What the priors do is, typical priors encode your prior knowledge. It will tell you what is the range of a parameter. That's a prior knowledge. What this prior does is it also gives you an idea whether certain physics is active or inactive. So if you think about dx over dt, what is my prior knowledge if dx over dt is actually in the physics or not? So that's why this is, I call it a little bit more ingenious than traditional priors. They use this method, they solve the problem, and I'll show you some results. So these are the true parameters. U dot depends on U and UV. V dot depends on V and UV. So they were able to recover the system accurately. They were also able to get the parameters very, very accurately. So the first coefficient was 1, they recovered 1.19, and so on and so forth. This works amazingly. The problem we realized later on was they actually cheated. They defined their prior knowledge based on the real system. So their prior distribution was centered at the true value. If you don't know the true value, this works horribly. So you can see if you don't know the true values, and we tried this, we actually spent 2 months trying to figure out why we are not getting the good results that the paper has. And the reason was they used a prior which was centered at the true values. And if you change that, it just looks bad, right? And again, the problem is it's not able to capture noise properly. I don't know if that's the best way to explain this here. But if we try to just use our approach with the same prior centered at 0, saying that this is an uninformative prior, we have no knowledge, everything is centered at 0, that's what this is referred as, we're able to accurately estimate the unknown parameters very, very accurately. So this was another example to show how the stochastic inverse models can be used. And this is another problem. I would not go into the details of this, but this is in collaboration with the professor at University of Arkansas. And we are trying to figure out if we can learn the physics of infiltration. Again, we have very limited time, so I'm going to skip this. But if you have any questions, please let me know. We tried on different types of material systems, those which has low viscosity. We were able to accurately predict in this case. For high viscosity, where you have these damping effect, again, we were able to predict the correct physics. Before I end, I do wanted to spend some time on what are some of the interesting problems and some of the things that I've been doing with Ankit here. So first problem is, I think I already mentioned this, the microtexture problem. This is with a colleague at Air Force. What they're really trying to do here is these EBSD measurements are costly. So they developed techniques that are much faster. They're called eddy current testing. You can do eddy current testing on large components. So the question that they're asking is, can we use eddy current data to figure out the electron EBSD measurements? You can see here that they look kind of similar. You see this big grain here is matching this big chunk here, but the specificity is lost in eddy current data. So can we solve an inverse problem to figure out the exact grain boundaries and the grain orientations? So that's one problem. Something that we did for last couple of years with Ankit is to understand the microstructure simulations. So I'm sure you must have done some type of a microstructure analysis, microstructure simulations. These are computationally very, very costly. Sometimes you have to run these simulations for days. So the question that we're trying to ask is, can we come up with intelligent or efficient representations of these microstructures so you can cut down all those time, or maybe somehow reuse your previous simulations to figure out what will be your simulation outcome for simulation that you probably will do 2 months, 1 year from now. So one of the first work that we did was this, trying to do a low dimensional representation of microstructures using tensors. And then once you're in the tensor space, now you can use your off-the-shelf machine learning models like Gaussian processes. So that was our first work published in MRS Bulletin. The second work was focused on a similar problem, but this is even better. What this says is you can run the simulation for a short period of time. You don't have to complete it. So if it takes like 10 days, you can run it for 1 day, and you can predict the data for 9 days by just looking at the data for 1 day. So it's in some ways you're extrapolating your simulations to predict the entire sequence of microstructure evolution. So it's done by Ankit's student here. And then one work that we are trying to do right now is most of these simulation models, if you think about it, they're forward looking. You plug in some parameters, you simulate it, and you observe what happens, right? But if you flip it the other way around, if you know what you're looking for, can you figure out how would you simulate this so you can reach the target? So that's the inverse problem also in the context of materials, microstructure evolution. We're almost on time. I just have 5 minutes. So I'm going to stop here and see if you have any questions.
All right. So thanks for the speaker. Great talk. Any questions? Maybe I can ask one.
Yes.
So interesting work, because it's good to see that you can actually interpret the more physical the mechanical properties, right, from elastic plastic properties from the indentation data, which is the force displacement. So my question is, is it possible to actually give it, instead of a data which comes from nano indentation, instead of that, we just give a microstructure? And
Yeah.
so because that's again a matrix, right? So, and you can obviously digitize it. So instead of the nano indentation as the data, can the microstructure itself be the data? And based on the training on everything, is it possible to get out a property?
I would say so. I think people have tried. There are multiple different areas of work on that space. I think the issue with microstructures is that they're very high dimensional. So whatever we are looking into, unless otherwise we have a statistical measure to quantify the microstructure, I think it becomes hard. But I agree with you. I think there are ways of doing that. Definitely, yeah.
Yeah. So if the data is three-dimensional,
Yeah.
like we're coming to the real crux of the problem. If the data is three-dimensional, whereas the force displacement data is probably a column matrix, a row matrix, or just a square matrix, for example, right? So if you're looking at a three-dimensional matrix, how difficult the problem becomes?
I think it's a complicated problem.
It is.
I think the main reason is we're going from a very high dimensional space to a very low dimensional space. So somehow we have to compress all that information into something that any machine learning model would be able to handle. I think that's the main challenge. How do we compress? So in this case, actually, I didn't say about this, but I'm doing what we are actually doing what Ankit is saying here. These dots actually represent one microstructure. So the idea is, how do we go from all of these high dimensional images to a single data point, and that still has all the information without, that is useful in predicting the properties.
That's the question.
I went way too fast in the last part, but if you have any questions, I am just right around the street. So you can definitely
reach out to me. Go ahead.
Anytime.
You can type it in or ask. I think it's just unmute yourself.
Introduce yourself. Yeah. Can you hear us over here at University of Arizona?
Yes.
Just had a quick question. So you use correlations between the force displacement and tensile testing. Do you think this can also be done with fatigue testing, with the force displacement testing?
Oh yeah, absolutely. Okay.
No.
All right. Thank you for your question. So the answer is, a short answer is yes. We are right now looking into residual measurement, residual testing by using cutting data, so or machining data just in general. So I would imagine that we can extend this type of an approach to more complex problems, looking into fatigue measurements or anything that we can somehow correlate with easy to measure quantities.
Hey, Asif, this is Krishna from UFA. We have to unfortunately log off. We have another thing coming up at 12, so we need to leave. So thanks a lot. Next time I'm in ASU, we should definitely catch up.
Thank you, Krishna. Thank you.
Thank you, Krishna.
The problems that work with, is it a thing that you just need to find the right method, or you just need 10 times, a billion times more data, or where do you think are the biggest hurdles in your research, and where it can be improved?
I can try to answer that question with this example. So even though data is the crux of AI, my philosophy is that you don't need a lot of data. We just need to understand the data, and you need to have the right data. And so a huge portion of my work focuses on active learning that tells you how you can collect data, collect informative data. So I'll give you an example here. Let's say I'm working with electron backscatter, and we want to figure out how we can predict electron backscatter by doing alternate measurements, right? So people came up with eddy current data. So I think the main question is, what is that measurement that I can do that has some relationship with what I'm trying to estimate? And that's the main question. So if I'm doing residual testing, I know if I do cutting or machining, the forces that are generated has a relationship with the residual stresses. So if I can measure the forces, I can somehow try to figure out the residual stresses. And that was the same motivation for indentation and stress strain. There is some elastoplastic response happening in both of these two processes, whether you do stretching or you do poking. Does that answer your question? So in a nutshell, I think we have to know what is the right data, and we have to understand how that data is related to what we are trying to predict. And so I say this to everybody, all of my students, do exploratory data analysis. You have to understand how the data looks like. And then only you can somehow associate it to whatever you're trying to predict or estimate. Thank you.